right. So, let's see. Am I recording? I'm recording. Am I heard?
Yeah, we can
Yep.
hear you.
All right.
We can
Good.
hear you.
All right. Perfect. All right. And I'm on the screen here. All right. So now we have a circuit that has two current sources, and we're given those in the time domain, and we need to find the steady state expression for I of t. So we need to find the current through the inductor, and I also added that to find the voltage across that inductor. Okay, so the first thing that we need to do is to change everything to phasors. So the first current would be 4 angle 0 degrees. We see that omega is 500. Our second current, let's change this to cosine, so that's 2 sine 500t minus 90 degrees. So that is 2 angle negative 90 degrees. And then our inductor will be J times 500 times 120 times 10 to the negative third, which is J60. And our capacitor, by the way, it really it seems silly, but when I started Circuits 2, I had never seen capacitors drawn like this, because in physics and in Circuits 1, they were always two horizontal lines, and it just confused me. But it's the sort of thing that people who are in electrical engineering all the time, they don't even think twice about it. But I know I was confused by it, so I'm just mentioning that is another way to draw a capacitor, and you'll see it both ways, just in case you hadn't seen it before. I know, actually, I think Mr. Rabelais prefers to write them like that. So the capacitor is minus J over omega, which is 500 times 20 times 10 to the negative 6. And that is minus J 100. So now if we redraw it in the phasor domain, I will have 4 angle 0, 50 ohms, J 60 ohms, minus J 100 ohms, 30 ohms, and 2 angle negative 90 degrees. Now, if you look at what we have here, our elements are not in series and they're not in parallel. But there's an easy way to fix that, and that is with source transformation. And I understand that a lot of you aren't real comfortable with source transformation, so let me just explain how you do it. If you have a current source, so this is kind of an aside. If I have a current source and a resistor in parallel, so this is R and this is I, that is equivalent to a voltage source and a resistor in series. And the voltage source will have its polarity with the plus in the same direction that the current was pointing, and this will be IR. Now, not as relevant for AC because the current is oscillating, but for DC it matters. And then similarly, if I had a voltage source in series, that is equivalent to a current source and resistor in parallel. The resistor stays the same, and the current will be V over R to get the value for it. You should never do a source transformation to try to find out information about the current source or the voltage source or the resistor that you're looking at. But if what you're looking at is somewhere else in the circuit, then you can do that source transformation to get to make your circuit a little bit easier. So if we look at our circuit here, we see that we have a current source and a resistor in parallel here, and a current source and a resistor in parallel there. So we can do a source transformation to change both of those to a voltage source and a resistor in series, and then we get a circuit that is all in series, which is nice. And so our voltage source on this side will be 4 times 50, which is 200. So our voltage source will be 200. And that was a 50 ohm resistor, yes. And so we'll just have a 50 ohm resistor. And then we'll have the J60 inductor. And then the voltage source on this side, well, 2 angle 90, 2 angle negative 90, that's the same as minus J2, because negative 90 is going straight down, that's on the imaginary axis, so that's minus J2. So minus J100 times minus J2 minus J100 times minus J2 is positive J squared 200, but J squared by definition is negative 1, so that's negative 200. So then this becomes a voltage source of negative 200, and we had a 30 ohm resistor. Oh wait, I've missed my capacitor was minus J100 and a 30 ohm resistor. Okay, so, and what am I looking for? The voltage, the current and the voltage across the 100 ohm resistor. 100 ohm. 120 millihenry inductor. Yeah, across the inductor. Okay, so for the current, it doesn't really matter. The current is the same everywhere. Notice I would have not really been able to do this if I needed the current through the capacitor or the current through the 50 ohm resistor, because I would have transformed those. Yes?
For the, I'm having brain fart. Oh yeah, whenever we do source transformation, can we treat capacitors and inductors the same as resistors?
After you've turned them into phasors.
Okay.
Only after you've turned them into phasors. Yeah, so once you've turned things into phasors, you can treat them like resistors. Anything that you can do to resistors in circuits 1, you can do to phasors. Okay, but we weren't looking for the current through the 50 ohm resistor or the capacitor. We're looking through just the inductor, which we did not transform, and so it's fine. So our total impedance here, so now it's nice because it's all in series. So our total impedance is 50 plus 30 is 80, 60 minus 100 is minus 40, so 80 minus J40 is our total impedance. And so our current, if we look at our total voltage here, so this side, this is plus, this is minus, this is plus, this is minus. And so if you think about our voltage here, our total voltage is going to have a magnitude of 400. If you come into this voltage on this side, you have negative. But that's not how you calculate. The sum is going to be 0, but the peak, the peak is 400 because when is it though? See, this is angle 0, that's angle 0, so it seems like
You said the peak 400?
oh, I see, yes. Yeah, so the peak is 400, and, yeah. So if we thought about adding together our voltages going across like this, so if I'm coming into this side, coming into the negative side, I'd have minus 200, and then coming into the positive side, I just read the number that's on there, which is minus 200, which gets me minus 400. But of course, it's AC, so we would have negative 400, positive 400, but the peak is going to be 400. So our current is going to be 400 over 80 minus J40. And that's going to be our current through the inductor and this resistor. And that ends up being 4 plus J2, which is 4.47 angle 26.57. Okay, so now how could I get the voltage across that inductor? So let's think about if I had a total voltage source of 400 and I had a 50 ohm and a J60 and a minus J100 and a 30 ohm. How could I get the voltage just across that inductor?
Voltage division.
Voltage division. And how would that voltage division work?
It's the source voltage times the target impedance divided by the series.
So it's my source voltage, which is a net 400, times the element that I'm looking at over the entire impedance. So I add those all together. And if I do that, I didn't do that, so I need to do that now. That would be 400 times J60 over 80 minus J40. Which is minus 120 plus 240i, and if I change that to polar, I get 268 angle 116.6.
Would another way to be is to find the current of that series, and then after that, since you find the total current, it's in series, so it's just gonna be the current times the inductor.
Absolutely, and since we have the current right here, we already solved for it. We could take that and multiply times J60, and that should give us the same answer.
Okay.
If somebody wants to check that real quick, it would make me happy. Actually, it'll make me unhappy if it doesn't work, so maybe I don't want to know. Now, the problem originally said to find the steady state expression for I of t, and I just found it as a phasor. So I didn't actually finish the current part of the question. So to put it in the time domain, I of t would equal 4.47 cosine, and then our omega is 500. 500t plus 26.57 degrees amps. And then my voltage, V of t, would be 268 cosine 500t plus 116.6 volts. Okay, any questions on this one? Yes?
I'm a little bit confused on how the voltage is 400.
How the voltage is 400. Okay, so let's say that we had a DC circuit. And I wanted to figure out what my total voltage was here. So going from here to here, I go up by 200. So I'm 200 more on this side. On this side, I know that the top is negative 200 more than the bottom, because this is negative 200, and so I know that the top here is really 200 less than the bottom, and so if I called this 0, I would need well, I can't call that 0, so I've got a resistor there. So, I mean, I can't, it's not 0 on both sides. What I know, let's slide them to where they're next to each other, and we can see it a little better. So if I have, okay, so if I slide this around over here, this side is minus, this side is plus. This is minus 200. So the plus side is negative 200 more than the minus side. So if I call this 0, this side has to be 200. And then on this one, this side has to be 200 more than this. It was 200 on this side, so this side has to be 400.
Oh, okay.
If they were 200 and 200, then our net voltage would be 0.
Or if the negative 200 polarities
Was switched, yeah.
Okay.
Is that,
Yeah, it's just a little tricky.
it is a little tricky. I had to think about it. I had to kind of wrap my mind around it too. Okay, other questions?
I just had a question, so I think I know the first one.
Yeah.
Would it be possible to do a mesh approach on this question? If we had like currents from left to or so, I don't know, just curious if that's possible.
Sure, and I will look at that in just a second. So absolutely, that would be possible. Give me just a second to answer this other question, and then we'll look at the mesh approach.
Can you go down a little bit? A little bit down. I'll show you a little bit. Okay, there you go. Whenever we're adding, because I know we're
Please
talking-
don't ask me about the 200 and the 200 voltage.
Well, no, it's well. Anyways, when simplifying voltage sources, I understand like when the voltage source.
Were you outside of the room when I was just explaining this, or were you just not paying attention?
No.
Because I just went over this.
Oh, never mind. I'll go to the video then.
Okay,
I was in the
okay,
bathroom,
okay.
that's all.
Oh, okay, all right, yeah, it's in the video.
Okay.
Okay, all right. All right. Okay, so mesh approach, and so since I'm gonna do this mesh right now, I'm not gonna do another one at the end, but let's see how the mesh would work on this one. So, okay, so we'll draw 3 mesh currents. And I'll call them I1, I2, and I3. Okay, you'd asked for mesh? I'm doing
Yeah.
mesh. Okay. All right, so I1 is I1, which was 4 angle 0. I3 is I2, which was 2 angle negative 90. Okay, so we'll just keep that in mind. Okay, so for our no, this is tough. So the reason I can't quite do mesh on this one
There's 2 current sources.
is the current sources, and I don't know, when you do a mesh equation, you're adding up your voltage drops, and I don't know the voltage drop across these current sources. And so while in theory I could do it, it's not.
You can do whenever you did your voltage, when you simplify your voltage sources, but I feel like that would be too complicated.
It would be too complicated, which is why I'm not going to do it. So I'm not actually going to do this one as mesh. So the idea was a good one, but then as we started doing it, we say, no, this is too hard, because I'd have to come up, and what the voltage would be here would be the same as the voltage across the 50 ohm resistor, but we don't know that yet. And we don't know the voltage across the 20 microfarad capacitor either. And so at this point it becomes, no, it's too hard to do by mesh. So it was a good thought, but it ended up not working. Did that answer your question?
Yeah.
Yeah, okay, you're welcome. If these had been voltage sources, yes, mesh would be good. Okay, other questions? All right.